Could you hear me? Okay, let's start. Okay. So, did you enjoy the first in-class practice? Any problems? Any questions? Okay, very good. So let's try to summarize what we have done since now and what we are going to do today and next lecture. So we have, first of all, introduced the general topic, what NLP is, what are the main fundamentals, what are the main issues and applications. We have completed the overview of the NLP applications. Of course, it was a high-level overview. We have not yet gone into detail. So we need now to deepen our knowledge on the fundamentals first, and then move to the application next. What we have done after the overview of the NLP applications is the description of the pre-processing steps. So what is traditional NLP data preparation? When you have to analyze some textual data, the raw version, the source, is commonly unsuitable for applying machine learning models. So you need something to improve the quality of the data to a large extent. So if, for example, you have to clean the data, you have to transfer the data in a suitable data format, you have to extract some peculiar information like entities, or you have to filter out some irrelevant, redundant features like words that are very, very frequent or meaningless according from a semantic point of view. So there are many steps that are established in NLP in order to clean the data. Now, what we do next is to describe the process of feature engineering, What feature engineering is, you should already know from the courses of data science fundamentals, is the step of creating features that will be analyzed by machine learning models, not only supervised models like classifiers or regression models, but also unsupervised techniques, for example, clustering or association mining. Our goal right now is to decide which are the potentially suitable representations for text, which can be adopted for solving complex tasks. And we have basically two ways to address feature engineering. One is customized and made feature engineering based on expert knowledge, based on our expertise, based on the feedbacks from a domain expert. And what is the traditional feature engineering process? You know what what are the main characteristics of a process, what are the key features, key properties influencing a given process, a given phenomenon, and then you can describe such a phenomenon using some quantitative variables that can be used in order to build your own data set, your own description of the data. So you have a set of samples potentially large, and you have a set of features that are the main descriptors of your data. Of course, who knows whether they are suitable or not for your next analytical processes? It depends on how good is your selection, how representative the features are, and how deep is your knowledge into the domain, the specific domain. Is this the only option? Of course not. You know that we have right now options, alternative options from the deep learning world, from the deep learning area. So in deep learning, the approach is the opposite. You don't have to do a handmade feature engineering step. You don't have to explicitly choose what are the features. You have to represent the data set in a way that can be handled by a neural network, and then let the network understand which are the features that the hidden features that are representative enough for solving a given task. So this is a complementary strategy. Is it suitable? It depends. It depends, of course, on the quality of the data, on the amount of data, because, of course, neural networks suffer from overfitting, have problems for training a neural network is not so easy. You need to cast a supervised process because neural networks have to learn in a supervised way. We will see later on in this course that there are strategies to self-annotate the data in a way that is suitable for representation learning using deep network. But of course, we have to, when we have to cope with textual data, we have these two options. There are scenarios, well-established scenarios, where textual data mining using traditional features works well. You already achieve satisfactory results. So if you don't have enough computational power, like for example GPUs, or if you don't have enough, if you don't have enough training data, this is the option, the only option you have, or this is the main option you have. But there are scenarios right now where, due to the abundance of data, of textual data, you have the chance to explore something else. And this will mean try to apply some embedding techniques, some transformers, some state-of-the-art models, which have shown to be more promising in terms of performance than the previous one, provided that some specific conditions, which will be the core part of this course. So today we will talk about the text representation. Actually, we don't go into detail of the deep learning-based approach, which will be the next topic. We focus on, first we address the occurrence-based text representation, which means representing data explicitly using some features, some selection of features derived from the structure of the text, derived from the pre-processing of the text, so which is mainly based on some syntactical models, like for example, vocabularies or synonyms. So you have you have already applied some NLP preprocessing steps, which provided you with a selection of, for example, of entities or words, filtering out stop words, of stems or lemmas. And these can be used to build your own explicit text representation, your feature value representation. We will call it feature value representation, which consists mainly in a relational dataset where rows are the documents in the most general conception of document. So a document can be the entire a complete paper or a section of the paper or even a single sentence, depends on the application. But rows are samples, then whereas columns are descriptors of your samples. Like, for example, the number of words, the presence of a given stop word, the presence of stop words, the presence of specific parts of speech, like the verb of the noun, the presence of entities. So these are features that you explicitly include in your data representation in order to allow the machine learning model to tackle specific tasks. And this needs to be done manually or semi-automatically by the NLP analyzer. Of course, this will be not the only option. We will compare the performance of this kind of traditional approach to machine learning with a deep learning-based strategy later on. So starting with the text representation, we have, sorry, I try to use full screen. Okay, we have the possibility to consider features related to the structure, not only to the content. So we have basically we can look into the content of the text, into the text, like for example looking at the part of speech, the syntactical dependencies, the parsing of the text, some syntactical properties which are dependent on the content, the actual content of the document. Or you can look at the structure of the document, which also provides some additional information about your activity. For example, you imagine to build your own data set, including a set of sentences. One possible feature describing that sentence, one sample, which corresponds to a sentence, can be whether the sentence belongs to the abstract, to the introductory section, to a method. If it is the first sentence, so the ordering of the sentence is the paragraph, the top sentence, the last sentence. These features are potentially relevant to your purposes. So you can build up your own features. You do feature engineering by also taking into account this kind of properties. Of course, this is less meaningful when you have to deal with unstructured data, like fully unstructured data, like, for example, if you have a tweet. No structure, no additional information. So you have to rely only on the plain text, the free text. There are documents that are weakly structured. It means that you have sectioning, you have the division of text into paragraphs. So you can consider such a division in order to extract your own features. You can also consider the content of the section, of the title of the section, for example, which can be deemed as a summary of the content of the section. This can be helpful also to filter out some irrelevant parts of the document, because you clean the data, you remove what is likely to be not informative enough. And there are also other representations like XML, JSON, HTML, which also provide some annotations. So not only the structure, the division is the division, but also the annotation. So you have a schema which tells you, for example, from this text span, from this point to this point, will refer to a specific metadata. This can be described by a specific metadata. Is written in boldface. So the writer put emphasis on this aspect or something like that. Okay? So depending on the level of annotation and the sectioning, you can also leverage such knowledge in order to effectively address specific NLP tasks. Then we will build a feature value model, which may rely either on the structure or on the content, or both, actually. And the level of granularity of the data you consider depends on the application. We have to choose which is the level of granularity of the samples. So one sample, one row of your table, of your data set, corresponds to an entire document, a paragraph, a section, a sentence. It depends. We will see several different applications according to the scenario. You must be capable of designing an ad hoc NLP pipeline. So this will be a skill that you need to have at the end of this course. And then you have also to decide the granularity of the features. So for example, if you have sentences, you may describe the content of the sentences according to features which work at the word level, single words, at n-gram level. So for example, which are basically sequences of n words in a row. You may consider entities or a combination of the above. So you may mix features related to different granularities, and this could be effective in some cases. This kind of approach is also useful for information retrieval purposes, when you have to retrieve some content based on some efficient data structures, like, for example, NoSQL DBs. If some of you is familiar with this kind of models, or like document-based or column-based DBs, try to annotate the data and exploit metadata in order to build efficient data structures, indexes, which allow you, for example, to aggregate, to compute some statistics efficiently and effectively. Okay. So the feature engineering part is what you should already know. We need, of course, to transform the data. Please. Oh, no problem. We need, of course, to transform the data to generate, to build a pipeline which semi-automatically builds your own features. And then, of course, this set of features, such a set of feature, can be also high dimensional. It's typically high dimensional because, for example, if I would like to consider n-grams, and all the n-grams occurring in the document the number of n-grams occurring in the document is potentially huge, is very large. So you need to typically reduce the cardinality of the number of features, reduce the dimensionality. You can do this in a smart way using some rule-based or domain syntactic-driven, some model-based approach, like, for example, looking into a dictionary of domain-specific words, looking whether they contain or not some specific, they are related to specific aspects, concepts that are pertinent to your purposes. Or, for example, you can look at the entities that are more correlated to a particular property in a given ontology. So there are ways to automate the filtering process, which are either model-driven or statistic-based. Statistic-based approaches to data reduction include approaches based on dimensionality reduction. We will see these kind of approaches later on in this lecture, so when we talk about topic modeling, because actually are the same. And we also have feature and selection approaches. You should already know something about this, because this will be a topic of the data science course. And the goal is to improve the quality, so get a simplified, a reduced set of features, so a simplified, more easily manageable data representation. The purposes of the dimensionality reduction and feature selection are a little bit different, so not exactly the same. Typically, dimensionality reduction is not necessarily addressed for addressing a supervised problem. Like I have 100 of features, I need to reduce the number of features in order to get improve the accuracy of my classification model, because the classifier, the network, is doing overfitting. The dataset is too sparse in order to achieve good performances of classification. But also when you are not doing predictions, classification, it can be also helpful to get a reduced data representation, for example, for visualization purposes. If you have a high-dimensional dataset, you apply clustering, and then you want to know whether your clusters are actually well separated from a graphical viewpoint. You want to show some intermediate results of your analytical steps. Dimensionality reduction processes like PCA or similar can be helpful to address this issue. And this can be helpful whatever the type of data you are analyzing, including, of course, textual data. You all have, of course, you can also distinguish between feature selection models that try to leverage the information about the target variable. So you want to predict something. If you want to do classification or regression, you have a class or a target you want to predict. And you can optimize the choice of the subset of features according to that target. Or you can do it in an unsupervised fashion, meaning look at the correlation matrix and I try to discard some features that are highly correlated with other features. So given a bunch of strongly correlated features, you choose a representative one, for example, and you discard the other. Okay, actually these are feature selection steps that are well known. Some wrapper, for example, you try to optimize the search for a subset of features. Filtering tries to apply statistical methods like correlation analysis, or intrinsic methods try to apply some dedicated algorithms. For example, you can apply decision tree models, which also embed some evaluation of the features in terms of, for example, Gini index, Gini score, or similar. Misclassification error, whatever. So these are standard feature engineering, feature selection steps, which are also applied on textual data as well. Okay, let's move to the core part of this lecture, which will be the occurrence-based representation, and then we have to introduce the first task, which will be topic detection, topic representation. Let me change the set of slides. I have already shared the slides on the didactic portal, so you can download the latest version of the slides. Probably we don't have time today to complete, to see all the slides, so we will, on Friday, we will complete this part, specifically the topic part, and we have a recap of neural network fundamentals, because they will be helpful to explain the deep learning based approaches to NLP. So on Friday we will conclude this part and have a recap of neural networks, which probably most of you are already familiar with this concept, but I think it could be helpful to recap these fundamentals. And of course, if some of you, some other students are from other master degree courses, have not attended the deep learning courses, this could be really helpful. Even to have some materials to learn the fundamentals and have basic knowledge about how a neural network works, how a recurrent network learning process works. So this kind of fundamentals. We will have, of course, a very short recap, no more than 2 hours, but I think it could be useful, especially according to the feedbacks of the former students, for the latter, this has been considered as helpful. Okay, let's start from the first topic, which is occurrence-based topic modeling. Sorry, occurrence-based text representation. Okay, here we are. Occurrence-based means that we are generating our features, we use and craft features according to the approaches that we have already described. We decide which are the potentially relevant features, and we build our own representation using a feature engineering step without deep learning, so using explicitly manually defined features. But these kind of features consist in this feature-based representation consists in a feature value representation, where given a sample, for example, an entire document or even a single sentence, you have a set of descriptors. Okay, so rows are samples, columns are features, which are basically descriptors of your data from a syntactical point of view, semantical point of view, section-based sectioning. So whatever kind of feature you can you think you want to consider. The most common approach to build your own representation is to put inside within a given combination of sample and feature a value which corresponds to a given occurrence-based statistics. Like, okay, I have a document, I have a word, I can put in the corresponding cell of my matrix 1 if the word actually occurs in that document, 0 otherwise. This is the simplest way to represent your textual data. This is called a document word representation or document term, it depends on but actually it's the same. Then this is the simplest way, like this. Okay, no, so here is, it could be misleading because here actually each document has at least only one word, but this is the formalization. Okay, so you take binary values. Each feature takes, for each sample, you assign a binary value per feature. 0, for example, if that feature is not present, like, for example, an entity recognized using an entity definition step, whether it is included in the document or not. And this is, of course, or the simplest version is just consider word level features. So words in a dictionary, for example, English dictionary. One column, one feature corresponds to a distinct word in the English vocabulary. And then, of course, some of the features, some of the words are not present in the analyzed documents, so they can be discarded from scratch at the very beginning. Then some other words are relatively frequent, so they occur in many documents. Some other occur only just in a few documents. So you put 0, 1, you build your own 0, 1 matrix. And this is a very simple representation, which of course lacks of information. So you miss relevant information. But this is extremely simple and can be also effective in some specific cases. This is related to the so-called one-hot encoding representation, which is commonly used in deep learning. But here we are not necessarily applying a deep learning network, a neural network model. You can simply build your own representation and apply whatever kind of model, like SVM or Bayesian model, whatever, okay? It's not necessarily related to a deep learning pipeline. What are the drawbacks of such a representation? it's extremely high dimensional. Let's imagine if you have one column per word in the Italian vocabulary. It means that you have thousands and thousands of words, thousands and thousands of different distinct features. So this means that you very likely incur in curse of dimensionality, because the model lacks of the very specific, the crucial information, because it's a too sparse representation. Many of the words occur just in a very few documents. So you have a matrix, a document word matrix, which is extremely sparse. So many zeros and then some one, whatever. So this is a problem. Of course, you can generate such a simple representation and apply then on top of this, apply some dimensionality reduction or feature selection step. This can be done, but of course, the representation, you should know in advance that such a representation is not the most rich, the most meaningful that you can have. You have more effective representations. One of the most popular one, which maybe some of you already know, because probably during the data science course they already introduced, it's called the term frequency inverse document frequency. It is extremely popular, even if it's quite simple. It basically focuses on evaluating two distinct frequency terms, and this frequency recalls the number of times a given item occurs in a dataset, in a collection. We analyze frequency from two different perspectives. One is document, the frequency within the entire collection of documents, so within the whole samples. So if you have, for example, a data set consisting of a set of documents, you describe data according to the words occurring in the documents, so document word representation. You count the term frequency, which entails counting how many times, in how many documents that term occurs. This is the document frequency. You also have a local frequency, which is a term frequency, which means how many times a given term or word, in this case they are considered a synonym, this term occurs within a given document. Okay, so you have a local, both local and global frequency evaluation. The local looks at the specific document, so the single sample, and you count how many times that word occurs is within that document. The global looks at the frequency globally within the entire document collection, but it's not like it counts. If, for example, if a word occurs 5 times in the first document and 10 times in the second one, the total is not 10 plus 5. The total is 2, because you count how many documents. Okay, so please look at pay attention to the formula. The term frequency, which is the local one, counts the number of occurrences of a word in a given document divided by the number of words in the document. So it's a normalized frequency. It's a relative frequency. Whereas the document frequency counts in how many documents that word occurs at least once. And this is I mentioned the document frequency because the document frequency tells you exactly it's comparable to the term frequency. Whereas in the formula of the TF-IDF score, the authors have proposed to use the inverse document frequency, because our goal here is to try to penalize those words that occur very frequently in almost all documents in your collection. So if you have 100 samples, and in 90% of that samples, that word actually occur, it is not discriminating enough. So it's not peculiar to a particular document. It's almost present in almost all documents. Like, for example, a stop word. A stop word is likely to have a very high document frequency. So removing the stop word here is beneficial, of course. But the goal of the inverse document frequency, so not positively contributing, but negatively contributing with the high document frequency, means that you are willing to reward those words that are relatively frequent within specific documents, which are, for example, that word is a keyword for a particular topic covered by these documents, but is not present in all the documents, because otherwise it's meaningless or less relevant to our purposes. For example, if you want to classify a document according to the word level content, you want to know whether some words are peculiar to a particular class, a particular category, and then if that word is present, you can assign with a certain likelihood that word, that category. And of course, if the document frequency is very high, the discriminating power of this word occurrence is almost near around zero, because it's not relevant. So, in conclusion, this kind of metric is suitable for analyzing, let me say, heterogeneous document collections. So documents that are not all pretty the same, because actually the content, the topics, what is covered by each sample should be heterogeneous enough, so diverse enough to have some peculiar local data distributions. Because otherwise, if it is all pretty the same, you will come into a different scenario where probably TF-IDF is not suitable for representing your data. We have, of course, alternative options. One is called term frequency, document frequency, and this is almost the same as the previous one, almost the same as the TF-IDF. But in DF, we remove the inverse, so we positively contribute with the document frequency term. It means that we reward words that are frequent both locally and globally. We have successfully applied this kind of variant of the TF-IDF metric in a summarization task, where, for example, if you have, let's think about news articles. So if you have the same news published described by many articles published by different newspapers, the same news means that the topic is almost the same, but some newspapers have, of course, emphasized some aspects, whereas others have not and neglected some other aspects and emphasized a particular one. So the words occurring are pretty the same, with specific differences. So in this case, to describe the general, to summarize the news content, it's probably better to focus on homogeneous metrics that try to reward, to leverage information from homogeneous collection. So ETF-DF is more suitable for representing homogeneous data collections. So there is no optimal weighting function. So the TF-IDF and the TF-DF are basically weighting function. So you have a matrix, like a document word matrix. You put a number in each cell of the matrix, and this is a weighting function. The weighting function is a weight which depends on the content of the document and the feature you are considering. And this, you have multiple options, not only TF-IDF, not only TF-DF. You have different options. You have to choose which one is the best for your purposes. For example, another extension of the TF-IDF matrix is called the BM25, best matching 25. And it is, the formula is here. As you can see here, you have again the two local and global terms, TF and IDF, similar to TF-IDF. It's a multiplication of two terms, TF and IDF. And as in the previous case, like here. So here you have the product of TF and IDF, which is the combination of the two. But the term frequency terms can be unbounded, so you may have some distortion according to when you incur in some heavily tailed distributions of TF of frequency vectors of frequency values. So, if in order to avoid such a distortion due to unbounded values, you may define an alternative family of scoring function, which is called best matching, which can be also weighted, so it can be also configured according to your needs. So, in a nutshell, we have this formula, which looks like a complicated formula, but it's actually a generalization of the previous one, where you count also, you have also this term called average DL, which means average document length. Okay, the length of the documents in terms of number of words, and over all the documents in the documents. And so you average the document length, and this term is as you can see, is the B times dj, which is the length of document j, divided by, normalized by the average document length. And you have this penalty score, B, which can be associated with the document length, which is a free parameter ranging from between 0 and 1. You can set up your parameter according to your needs. And this allows you to mitigate some negative effects due to the frequency value distribution in your data. Is it the only option you have? Of course not. Basically, the standard approach is to define, based on your needs, a term frequency term, a document frequency term, and then combine the two. This is established, okay? Of course, you can figure out some even alternative strategies, okay, whatever, but it's less common. What is commonly used in NLP is to define your local frequency term in an occurrence-based representation, define a global frequency term, and then combine two in a way that is typically just a product or a linear combination. Here we have some, I reported some examples of term frequency and also some examples of document frequency. Okay, if you Google, if you look at some books, you can find even other alternatives. Of course, you are not expected to know just all the possible combinations, just the most relevant ones, the most famous ones. I can just briefly summarize what are the key points of this kind of metrics. And the three aspects that that are worth considering are these. First of all, you can try to have log normalization. So use the logarithm as usual to normalize the distribution, the weight distribution, like in this term. I can show you, like here, the smooth version of the document frequency. This is typical in many machine learning statistic-based approaches. The other is to bound the range of variation of the frequency values, and this is the case of the BM25 function, and also not only BM25, but also other like this. Yes, so it's like not allowing putting a boundary at the distribution of the frequency values. with normalization or similar. And finally, you have also to decide how to let domain experts or users to configure your system. So how many parameters? This is not trivial because when you have to design your pipeline, you of course have some degree of freedom, and it means that the user can set up some parameters, can optimize some parameters according to the analyzed data distribution. And of course, the less parameter you have, the better, the more usable the system is. So there are some systems that try to, some versions of the weighting function that have just one free parameter, the other they have two, others have no parameters, but of course, it's hard to find a metric that works in every possible context. So basically, it's almost impossible in my opinion. For example, going back to the simplest case, TF-IDF, what happens if I have to, so we are here, let's go back here. What happens if we have to analyze tweets? What happens to the TF-IDF distribution? Twitter messages. What would you expect from the distribution of the frequency, the term frequency, the document frequency values in a Twitter distribution, Twitter dataset? Which score, term or document? Okay, the term is always equal to 0 or at most 1. So the frequency, how many times, what is the likelihood of having the same word occurring many times in the same tweet? It's almost 0, except for some articles or prepositions, some stop words that you can filter out during the processing stage. So actually, in most cases, except for particular cases, what is dominant in this case is the document frequency, which means in how many tweets you find a specific word, a specific n-gram. Because the text is too short to have actually a local frequency above 1. So just you count just no occurrence or at most one occurrence. Is it clear? Okay. So this is a typical scenario where you have to think about what you expect and design your own metric, which can be also alternatives, or probably actually this kind of weighting function is not suitable for Twitter messages. For this reason, because we have one term which is negligible, actually. Okay. Okay, if you want to read more, I suggest you to read this book from Manning book. This is a professor at Stanford. It's not mandatory, as I told you. The additional readings I provide you this academic year is an additional suggested recommended read. So you're not expected to know everything which is not covered by the lecture, but is included in the book. But of course, it's also another way to explain, another way to describe some more examples. So I think it's helpful. So it's also free, so you don't have to pay. So here is the problem. In most NLP scenarios, the problem is that you are very likely to incur in a course of dimensionality issue, because the number of features is impressive. Even whether you consider just single words or 2 grams, you have an impressive number of combinations. And further, if you consider other features, like, for example, the number of symbols, the number of verbs or nouns doing part of speech tagging, so the problem makes even more complex. So this is one of the main problems. And the other is that what I've shown you until now, except for a few cases, for example, the entity recognition process, mainly highlights the properties of the text that are dependent on the syntax. Like, for example, how you write a specific word, if it is a plural or a singular form, if they have the same stem of the same lemma, if there are dependencies between words and a noun and the adjective, if the word occurs in a domain-specific dictionary, and so on and so forth. These are syntactical properties of the text. Is it enough? Probably no. In many challenging tasks, for example, machine translation, for example, summarization, for example, AI chatbots, so conversational agents, this is definitely not enough. Because what we have to capture is actually also the semantics behind the text. So, for example, king and queen, using an occurrence-based representation, are likely to have a different representation. So the vector corresponding to the values, the numbers you have in your matrix, can be, even whatever kind of metric you use, they can be extremely different. They can be different because it's not dependent on the semantic meaning of the word. So what is the information, the meaning, the message conveyed by the text is not represented by the syntactical features. Also, you lose something, which is crucial in many natural language understanding applications. So what we will do, and we will address from the next week on, is to try to apply some, to build some neural network-based representations, some latent features, generate some latent features that try to preserve some semantic properties. So to put, in a nutshell, we will build our representation, high-dimensional representation of features, where features are not easy to interpret. So we have not a column corresponding to the number of symbols, a column corresponding to the occurrences of word, car, and so on and so forth. You will not be able to interpret the meaning of a feature explicitly. You have some artificial features describing your data, and you use that features to represent your piece of text in a space, in a high-dimensional space, which has been generated using neural network models. This space loses some interpretability features, let me say, because you are not able to interpret the features. You're not able to say, okay, that feature is not relevant, this feature is more significant than this, according to your domain expert view. But you have significantly more expressive properties from a semantic point of view. So this model is able to put together, or at least close each other, two words that are semantically related to. This will be the key point. We will describe this from next week on, because this will be not the occurrence-based approach, but it's the neural network-based approach. Okay. So this closes the presentation of the occurrence-based approach. Now we will open a new topic, which is topic modeling. Okay, sorry for the. What is the topic modeling? I have enumerated the topic modeling in in the list of NLP application, because it is actually an application. It finds application in many real contexts. The idea is to describe the topics covered by a collection of documents, or even a single document if it is complex enough. The simplest case is the word cloud. What is a word cloud? A word cloud is a picture showing the words that most frequently occur in a document. The words that are the top frequent words are written using a font size, a higher font size, so that the user, the end user, can immediately catch the underlying topics, the underlying trends in a collection, like for example, in a collection of Facebook or social network messages or whatever. Of course, this is a trivial approach. There are many different solutions that try to improve these kind of approaches. I will show you a couple of established or traditional approaches to topic modeling, and then if we have time later on, we will present also some new and more recent approach. But we will focus now on two actually established approaches to topic modeling. One is called latent semantic indexing, and the other one is called LDA. Let me show you here. Okay, latent distributed allocation, LDA. So the acronym are LSI and LDA. Okay, so these are the two main approaches, not the only ones. I will describe the main concepts behind these two approaches. And of course, I will also highlight the drawbacks of these approaches. In order to present you also the extensions, I need also to introduce the deep learning based approaches. So we can, after introducing the embedding models, the representation, the transformers, we can go back to this topic and describe more recent solutions. But let's start from the simplest one, which are also still used in recent applications. So it's not So what is the idea? The idea is to try to obtain a topic level description of your data, to capture some topics which are latent, which are not explicitly mentioned in any query, because the problem of retrieving content from a query is a different story. It's information retrieval, as I told you during the past lectures. Here we are commonly in a fully unsupervised scenario where you don't have annotated data. In most cases, you don't have a query, so you just have a collection of documents, some parameters just to set up your model, your algorithm, and that's it. You have to produce as an output a description of the documents. And what the LSA and the LDA do is to provide a word level description of the documents, which is not simply a frequency-based model, but is something that is more complex, more elaborated. One is the former one, LSA, is based on a matrix factorization approach called a singular value decomposition. The latter is based on a probabilistic generative model. Both provide you with a set of topics, each one described by a set of words. So you know the topics and the corresponding description, word level description. The words that are are mainly described in that topic are A, B, and C. Of course, these are two completely different approaches. they have pros and cons. Again, we don't have a clear winner. We have pros and cons of each of them. The idea of a word level description is that typically, even if the documents are complex, with complex structure, the underlying topics covered are relatively, and the number of underlying topics is relatively small. So you are able to summarize the documents just focusing on the key words representing a given topic. Okay, let's start from the first one, which is latent semantic indexing, which relies on a mathematical approach for matrix factorization. Basically, in a nutshell, you have the occurrence-based data representation. Let's think about the document word representation with binary values, with TF values, whatever. But you have a matrix, okay? Documents and features, typically words, okay? You can generalize to n-grams or whatever, but let's start from the simplest case. Documents, words, a matrix, which is typically a knot, which has some notable properties, which is rather sparse, full of zero, or the distribution is not uniform at all. So you have to capture some portions of your matrix space, which are some interesting properties. And you do this using this matrix decomposition called singular value decomposition, which is based on some fundamentals of geometry. I don't know if you remember this. This is the typical decomposition used for decompose square matrix. The square matrix here is S. You can decompose it and define the so-called eigenvalues and eigenvectors. Okay, this can be done under some mathematical conditions. Actually, this is not this is out of the scope of this course, but this is for square matrix. Is this the case for NLP matrix? Are we handling square matrix? In other words, are the number of documents you are analyzing, is it the same as the number of words? Not at all, because the number of words is orders of magnitude higher than the number of documents. Even if you consider sentences and not entire documents, you have many sentences, okay, but you have so many words, so many n-grams, so many other features you can derive from the raw text. So typically the dimensions are really different. Okay, let's go on. If you have a m times n matrix, so it's here we are in the non-square matrix case, you can decompose your matrix using SVD, singular value decomposition, according to such a decomposition, where sigma is a square matrix, where you have just non-zero values in the main diagonal, and that non-zero values are actually the so-called eigenvalues, or their eigenvalues. I can show you here. Here, okay. So the eigenvalues are lambda, and the lambda values are the non-zero values of the diagonal matrix. The diagonal matrix is sigma, where that values will indicate the relevance of a given topic. Okay? We will come up with a reduced version of this decomposition, which will tell you, okay, we have a topic which has a relevance equal to that specific value sigma. Sigma is actually the square root of the eigenvalue. Okay, so sigma is uppercase sigma is a diagonal matrix. Okay, composed of non-zero values, which are sigma lowercase sigma. Each lowercase sigma, like sigma 1, sigma 2, sigma 3, weights the importance of a given topic. Okay? Then you have other matrices, because the decomposition of the original matrix A, which is your document term matrix, is a product of three different matrices: U, sigma uppercase, and B transposed. Okay? So this product is a decomposition of the original one, which is instrumental for our purposes. Lattice semantic indexing is commonly used for topic modeling, but also for dimensionality reduction, as we see. Because yeah. Okay. Actually, this technique, which has been also used for dimensionality reduction, will be also applied for topic modeling. We will see now how to achieve a word level representation of the topics starting from the singular value decomposition of the document word matrix. So let's start from the matrix A. So A is the document word matrix. Documents as samples, words as columns, features, and the values are, for example, binary values or TF-IDF values. Let's start from binary values, okay? You get this representation, and this can be achieved, as we will see later on, in an efficient way. They are efficient, even parallel implementation of the SVD decomposition in many different languages, programming languages. You achieve this representation. The core part is this sigma matrix, which is a diagonal matrix, which includes as non-zero values the sigma values, which are the eigenvalues, the square root of the eigenvalues. For our convenience, we can sort the eigenvalues in a decreasing order. So the ones occurring in the first row, the top row of the diagonal matrix, will be the most important topic. Sigma 1 is the higher than sigma 2, then sigma 3, and so on. And then we will apply the key step of the dimensionality reduction process, which entails reducing the dimensionality of the matrix, getting a low rank representation. So you want to achieve, to get a simplified, a reduced version of the original one. AK is a matrix of rank K, which is not which loses some, you lose some information with respect to the original one, but you get what it reflects are the main properties, which are representative of the underlying topics. Okay, so you apply dimensionality reduction. This approximation means that you find a K approximated reduced version of the original matrix of rank K, such that you try to minimize this error, this reconstruction error. Actually, the norm of the error. So here is the formulation. So what you would like to have in your reduced representation is to retain most of the salient topics. So of course, if you want to produce, to build a model that describe your topics, you need to make some decisions about what the most relevant topics are and what are instead the secondary, lowly relevant topics. So how to choose which are the most relevant topics? According to the values of the eigenvalues. So we have already sorted the topics in decreasing order in terms of eigenvalue. So basically the top eigenvalues represent the most important topics. So we can truncate our diagonal matrix. We can reduce to 0 all the eigenvalues and then the corresponding eigenvectors, so we will see now, because we neglect all the topics corresponding to an eigenvalue which is too small. Okay? We get the simplification, which is of course not error-free. So you will do some approximation. But the approximation is sigma k1, k plus 1, where k is the number of topics you want to describe. Okay? We want to describe k topics. Actually, we can decide, okay, we focus on the top 2 topics in our collection, which is a little bit arbitrary, because you don't know in advance whether the collection contains exactly 2 topics. But there is also an empirical method to choose the optimal value of k, the likely optimal, quasi-optimal value of k. We will see it in a minute. The reduction means, you look at the upper representation, level representation. In the diagonal matrix sigma, you reduce to 0 all the terms in the matrix, because you neglect all the topics that have little importance in your choose collection. So all the sigma with k plus 1, k plus 2, k plus 3 are reduced to 0. So you have to, of course, in turn update all the other values in the matrix decomposition. And you will come up with a representation which is a reduced version or low rank representation of your data, original data, which preserves the word correlations describing the most relevant topics. So here is the representation. Of course, as you can see, to achieve the correct result, you also reduce to 0 part of the other 2 metrics, which are not diagonal metrics, and which tell you basically which are needed to compute the relevance of a word with respect to a given topic, or the relevance of a document with respect to a given topic. More specifically, this I can show you. Okay. Once you get the reduced version, so the one where, the gray version, the gray part of the matrix is 0, all zeros, okay? You keep only the most salient part, which is non-gray, white part of the matrix. You get an approximated version of the matrix. In the previous version, it's called AK, here it's called A prime, but it's something different from K. It's a simplified version of A. You keep only K topics and K corresponding eigenvalues. What about U and V transposed? They provide you very relevant information, because, okay, from the diagram, you know sigma 1, sigma 2, sigma 3, so the relevance of the overall relevance of the topic. But from the V transpose and U, you have the information about the relevance of each document with respect to the K most significant topics. So, for example, the first one corresponds to the relevance of one particular document to a particular topic. We assume that a given topic may cover multiple, a given document may cover multiple topics. It's reasonable. It would be unrealistic to say each document has one topic, only one topic. One document, many topics potentially. One word can be representative, can be used to describe many topics. So you have a many-to-many relationship between documents and topics and words and topics. Okay? One word, many topics potentially, one or many, or even none, in case. One document, potentially many topics. And you want to know, okay, given a topic, what are the most relevant topics to that topics? What are the documents that are most likely relevant to that topic? If I want to know everything about a given topic, which documents in my collection should I explore? Okay? And what can be seen here, if you look at the top K rows, K is the number of topics I have selected, which corresponds to the number of eigenvalues. If I look at, for example, the first row, I know that the importance of a given document for that particular topic. So the most relevant topic, the top one in the short list of K topics, covers the document 1 with relevance 0.5, the document 2 with relevance 0.9, the document 3 with relevance 0.1. Okay? So if you want to look at the documents that mainly cover that topic, you can neglect, for example, to read document 3. Is it clear? The same reasoning can be applied at the word level. So if I want to describe a topic, which are the words that are most relevant? Which words should I consider? I need a description, a word level description of a topic. I can U matrix, which tells you the importance, the relevance of each word with respect to each of the K most important topics. So, for example, here you have the words and the documents. You have a 1-0 binary matrix. You have these numbers. According to the diagonal matrix, you know that according to this reduced version, the main topics of this collection are 2, because actually we have already reduced the matrix and you get only 2 non-zero eigenvalues. One takes values 2.16 and the other takes value 1.59. Of course, the first one is the most important one. We usually sort them in decreasing order. And then you want to know, okay, given the topic represented by the first eigenvalue, 2.16, which are the documents that mainly cover that topic? Or which are the words that can describe that topic? Because, of course, some of the words in the collection are not representative of that topic, and some of the documents actually do not cover that topic. You can explore V transpose and U to address this issue. But first, before doing this, let's try to look at to consider which is the optimal K value. Because if you have a matrix here, the original value, the original version of the decomposition, you have the document word representation. You apply the SVD, you get the decomposition of the original matrix. Without doing any reduction, it may be the case that the diagonal matrix contains many non-zero values. Okay, not only 2. 2 is of course, the optimal case, just very summarized description of your topics, just 2 topics. But in some cases, you get 10 topics, 15 topics, whatever. So the matrix is not full of 0 in the diagonal. So you have to reduce. Which reduction should we apply? We can look at the series. You sort the eigenvalues. You look at the decreasing series of values, of eigenvalues, and you reduce to 0 those eigenvalues that are, you find the eigenvalues, the value whose value is below the half of the preceding one. Okay? So, for example, here, in the original version, I could have, if I have 2.16, I look at the second one, is it more than the half of 2.16? 2.16 divided by 2 is 1.08. So the value of the second eigenvalue is higher, 1.59 is above, is higher than 1.08. So the second topic is relevant enough to be kept in the reduced version. If we find, for example, as a third eigenvalue 0.4, we divide 1.59 divided by 2, we get a value which is 0.78, which is above the threshold, which is 0.5. So we remove 0.5 because it's not relevant enough. And the same for all the remaining topics. Is this an exact approach? Of course not. It's an empirical heuristic method which can be applied in order to automatically configure the parameter k. If you already know, for some reasons, in your application, what is the actual number of topics, please use it, okay? If you know in advance that you are looking for k equal to 5 topics, okay, use it. Use k equal to 5, because you know something, you have a priori knowledge on your data. But if you don't have this, and this is the typical case for topic modeling, you can apply this empirical method. Okay? Sorry, probably I'm a little bit late. We can complete this part on Friday, and then we will move to the LDA part. We have also some exercise, a couple of exercises to fix these concepts and clarify this process.